Hello and welcome you all to the NPTEL MOOC on Applied Electromagnetics for Engineers. In the previous module, we looked at solving Laplace's equation in one dimension. Thereby, we also derived the capacitance of a parallel plate capacitor and a coaxial cable. In this module, we will first solve Laplace's equation in two dimensions and then solve Poisson's equation in one dimension. Now, my main motivation here is to introduce you to a technique called as variable separable method, which we will adopt later on for solving such two-dimensional problems. Along that way, I will also show you how and what type of functions are necessary in order to satisfy Laplace's equation once the dimension of Laplace equation becomes two-dimension from the simple one-dimension case. So let us begin by looking at the problem chosen to illustrate how to solve Laplace's equation in two dimensions. You have a top conducting plate. For now, assume that the conductivity is very nice, it's about infinity, and then there is a bottom conducting plate, okay, and these two plates are actually joined together. Now in electrostatic phenomenon, which is what we are dealing with here, you should remember that the electric fields that are going to be set up by this parallel plate structure will be time invariant, that is, it won't be varying with respect to time, and for that reason only we are able to actually define the potential or the voltage V between the two strips unambiguously, right, which also means that the conducting plates themselves are the surfaces of constant potentials, okay. So this phenomenon of equipotentiality holds only in the case of static condition, and it will not hold in the case of a time varying situation such as a transmission line that we have studied in the first part of the course. Nevertheless, coming back to the problem at hand, you have the two plates. We will again assume that the plates actually have quite a bit of a width and length, okay. So we are not bothered what happens at the edges of these plates, that is, we will neglect completely the fact that there will be some edge effect in dealing with the problem over here. What we now do is we join these two plates. So essentially both are at the same potential, the top and the bottom potential, and then we imagine that we actually have inserted a strip at the middle of the two plates, okay. The strip of course has to be inserted in such a way that there actually has to be a small gap at the top. So let me rewrite this one over here. So there has to be a small gap here which we will be filled with an insulating material, otherwise everything will be at the same potential, okay. So we need to give a small insulating gap, as we call this one, okay, and leaving this small insulating gap, you have a metal strip that is been connected in the center, okay, and this axis essentially goes very long. So you can think of this as the z axis, and we consider that the z axis is quite long, and therefore what we want is what happens not along the z axis but what really happens along the y axis. So what is that condition that we are forcing with the strip? We have joined the two plates, the top and the bottom, and then we hold that two plates with respect to a certain potential difference, which we call here as V0, okay, where the other point is connected, the source is connected to the metal strip in between. So in other words, the metal strip is actually at a higher potential V0 than the two plates. You can even imagine that the two plates are situated at the ground potential or 0 volt, and the strip is actually at a higher potential of V0 volt. And what we want is this situation. So we have a strip in this way, okay, and then we have this direction along which this particular plates are going. So this is my x direction. So essentially look, what I am looking at is in this particular cross section. So this way is the y direction, and there is a certain gap over here, as I told you, and this fellow is kept at a potential V0, the strip is kept at a potential V0, and what we want is a potential or the voltage V as a function of x and y, okay. The top and the bottom plates are of course at 0 potential. So it is essentially that you are looking at it from this particular point, and then this view is what is relevant over here, okay. The z axis is not relevant over here. We are interested in what is happening to the potential in between this region along the length x, okay. Now that we have set up a problem, we clearly understand that this problem is a two-dimensional problem, correct. This is a two-dimensional problem because if you just go by the physical understanding of what the potential means, by placing a higher potential at one conducting plate and keeping the other plates at 0 potential, what I have created is a potential difference between the two. And whenever there is a potential difference, okay, we know that there will be an electric field between them, and we also know that the electric field likes to go from the higher potential to a lower potential. Therefore, you can expect, we will later show that this is correct, but you can expect that the field lines will actually go like this. Okay, so the field lines will go like this, and the potential being 0 at the center, right, and it would be at a potential V0. As you go away from the x axis, that is, as you go away and away, you can actually see that the potential would go something like this. The potential will be 0 at the center, and then it will keep going away as you go along the x direction. So these red lines are essentially the field lines, and the green lines are the constant potential contours that I have drawn. Clearly they have to be perpendicular to each other from the operation of the gradient thing, right. So we know that this is essentially what physically would be happening. So you have these constant potential contours, and piercing them at normal will be the electric fields that you are going to find. Okay. Now, how do we obtain the same things using mathematical relationships? For that, we need to solve the second, Laplace's equation in 2 dimension. We already know what is Laplace's equation applied in the region in between the two plates. So at any point x and y I pick, the corresponding Laplace's equation is del square v equal to 0. So rewriting this as the partial derivative, that is expanding this del square, you have del square v by del x square plus del square v by del y square equal to 0. Now we also know that it is not just enough for us to solve the equations, we will eventually have to apply certain boundary conditions in order to obtain a unique solution. So I also need to tabulate, or I also need to give you what are the boundary conditions that I am actually going to apply to this problem. Clearly you have a top wall and a bottom wall. So at the top wall and the bottom wall, the potential V must be equal to 0. The top wall is at y equal to, let us call this as y equal to a, and this one as y equal to 0. So these are the two surfaces, or two lines which tell you the top which is at y equal to a and the bottom which is at y equal to 0. So at both walls, that is at y equal to 0 and at y equal to a, for all values of x going from, so let us assume that x is 0 here, and this is how the x axis is going around, so along the horizontal direction. So for all values of x such that x is 0 less than or equal to x less than or equal to infinity, the potential must be equal to 0. So potential of V at x, y can be 0 or y can be a. In both cases the potential has to be equal to 0. So this is a stupid mathematical notation that I have used. This is my own, so don't get confused. What it is saying is two conditions. It is saying that V at any point x along the axis or along the direction of x, on y equal to 0 bottom plate and y equal to a top plate, the potential there must be equal to 0. Where else do we have a potential condition? Well, we consider what should happen at a very large x. So as x tends to infinity, you do expect the potential V to go off to 0, right. So potential V goes off to 0 as you go very far away into the condition, and y of course is limited by 0 to y less than or equal to a. Okay. Then there is one more condition, the final boundary condition as you might want to think of, and that boundary condition happens to be on the left wall over here, at which we have kept the potential to be equal to V0, that is at x equal to 0 and y between 0 to a, right, though we have an insulating gap out there. So y 0 to a, the potential V is equal to V0. So this is the final boundary condition that I actually have. So subject to these boundary conditions, we need to solve Laplace's equation. What I am going to do is actually to skip a few mathematical details. Okay, I actually expect that you will fill in those details while yourself, because there is nothing else like actually solving the problem along with the lecture. Okay, you can pause and then fill in all the details, and you will see that all the equations that I am writing, you can derive it for yourself. If you are able to do that one, then you have understood this particular problem, how to solve it. The reason why I want to do that one is because I want to also cover Poisson's equation in this same module. Okay, I will give you basic equations and then tell you what you need to do in order to arrive at the next step of the equation. So we go back to the second order partial derivative equation, and we recognize that in order to solve this one, right? It's not just enough that I consider v is some function of x or some function of y, because v in this case happens to be a function of both x and y, and this function is completely unknown to me. Okay, I only know the boundary condition, and so how do I actually try to solve it? I can't directly integrate it, because if I integrate the left hand side, then I don't know how to integrate on the right hand side, because I don't know how this function would actually change as a function of x and y. Therefore, I can't integrate the equations directly, right? So the direct integration method doesn't work. What we do is what is called as the variable separable method or separation of the variable method, in which we assume that the unknown potential v of x y, okay, satisfying this equation, can be written purely as a product of two functions, one of which is varying only with x and the other one is varying only with y. So you have to distinguish here by the capital X and the small x. Small x is the variable, capital X is actually the what we are denoting as a function. I could equally have taken this as f of x and g of y, but this is a common notation that we use in variable separable method. This reinforces that the product solution that you are looking for is composed of a function only of x and a function only of y. Now substitute this one into this expression. So if I now differentiate partially with respect to x, this potential v of x y, I see that because I am looking at a differentiation with respect to x, I can treat y of y as a constant, and differentiating x with respect to x will give you the derivative of x. So I don't know that one because I don't know how it goes, and please do not confuse that d by dx of capital X of x is equal to 1. This is not correct. Okay, so please ensure that this is not correct and you are not making this mistake. Okay, because x is just a name of the function that we have chosen, it is not equal to small x. There is a shorthand notation for writing this. This is actually equal to y x prime, where x prime is one of the ways in which we write dx by dx or d by dx of x. Similarly, if I now differentiate the above expression once more with respect to x, I will obviously get the second partial derivative of v with respect to x, which you can clearly see will be equal to y x double prime. By the same logic, del square v by del y square will be equal to x y double prime. So now you substitute for del square v by del x square here and del square v by del y square into this Laplace's equation. So obtain x double prime y plus x y double prime is equal to 0. Okay. Divide both sides by x y, and while dividing this I am assuming that the product x and y never goes to 0. Okay, otherwise this division will be in a bit of a problem for us. So when I divide this one by x y throughout, what I obtain is x double prime by x plus y double prime by y equal to 0. Now the crux of variable separable method is here. This term x prime by x is a function only of small x. The function here is y double prime by y is a function only of small y. Now how can I have one function of x and another function of y? I mean, they could be, for example, sine square x, this could be some Bessel function of y, it could be any crazy type of functions that I have, but how can two functions at every point x and y sum up to 0? The only way it can happen is when this function x of x is a constant and the function y double prime by y is the same constant except with a minus sign, right? Because any constant minus a plus a will be equal to 0, right? So clearly this x double prime by x must be a constant and y double prime by y must be the minus of the constant, and in the to simplify matters, we consider this x double prime by x to be the separation constant k square. K is called as a separation constant, and this should actually be equal to minus y double prime by y. Okay, only then that the sum of these two will actually go to 0. So you now have two ordinary differential equations. So you have x double prime equal to plus k square x, and then y double prime is equal to minus k square y. The general solutions for these are the exponential functions, or they are the sine hyperbolic and sine functions. I will use the exponential solutions over here. Okay, so I can find the general solution of x of x satisfying this ordinary differential equation as some constant c1 e to the power kx plus c2 e power minus kx. Okay, assuming that k is a positive quantity, so these are the solutions for x. Otherwise you can also have the solutions in the form of sine hyperbolic and cos hyperbolic functions, but we will not consider this because we are not really familiar with sine hyperbolic and cosine hyperbolic functions. Similarly for this one, because there is a negative sign out there, the exponential terms will become imaginary, that is y of y will be equal to some c3 e power j k y plus c4 e power minus j k y. Okay, and remember that actual solution v of x y is a function of these two, or is a product of these two, which is c1 e power kx plus c2 e power minus kx multiplied by c3 e power jky plus c4 e power minus jky. I hope you have followed the thread throughout here, and now what we need to do is to actually apply boundary conditions. Okay, let us apply a boundary condition which tells us that you can of course also expand this one, right. So you have an c1 e power kx, and then you have a c2 e power minus kx, there is a e power j ky, so you can expand and then add the exponential terms, and you can kind of simplify what you are looking at. But if I leave it as it is also, that is perfectly fine. So first I will apply the boundary condition. So this is the part where I am applying the boundary conditions. Okay, I apply the boundary condition that as x gets larger and larger for all values of y between 0 to a, this potential must be equal to 0. Now examine which is the x dependence. So this is the x dependence. As x is made larger and larger when k is positive constant, so unless c1 happens to be 0, this term will keep on increasing, right. So this term will keep on increasing and eventually goes off to infinity. Then you don't get any meaningful solutions for that. Therefore, because we want the potential and the electric fields to be remaining finite, we consider, or we take the obvious conclusion that c1 must be equal to 0. So the condition that potential must go off to infinity will allow me to say that this is actually equal to 0. Okay, now you can kind of simplify what you are going to get. Okay, so you can now simplify this expression. So you get v of xy is equal to some c2 c3, I am just opening the brackets and multiplying each of them. So you have e power minus kx e power j ky plus c2 c4 e power minus kx e power minus jky. Now we also know from de Moivre's theorem that e power j theta is nothing but cos theta plus j sin theta. So I can apply that to these complex exponentials e power jky and e power minus jky, and then write the potential as some c1 prime, where c1 prime will be equal to c2 c3 c1 prime e power minus kx, and write this as cos ky plus j sin ky, okay, plus c2 prime, where c2 prime will be c2 c4 e power minus kx, and this is cos ky. However, here you will have a minus j sin ky. Okay, so this is the solution v of xy that we have. Now we still are left with a couple of additional boundary conditions that we need to specify. Now what happens at y equal to 0? So at y equal to 0, we know that the potential for all values of x must be equal to 0, right. So now you substitute what happens at y equal to 0, you will immediately recognize that it is the cosine term which actually becomes unity, but the sine terms go off to 0. Okay, so when you see that, for what you are going to get, the sine term will go to 0 and cosine term will become equal to 1, and what you get here is c1 prime plus c2 prime e power minus kx must be equal to 0. Now under no condition we have the case that e power minus kx is 0, that is we can evaluate this one at x equal to 1, x equal to 2, and then see that this has to be non-zero unless we take x equal to infinity, but we have already considered that condition earlier. So we keep x finite and recognize that the condition y equal to 0, v equal to 0 is telling us that c2 prime equal to minus c1 prime. Similarly, at y equal to a, potential is again equal to 0. From the previous step you can show that v of xy would have reduced itself to some j, some c1 prime e power minus kx, and it would have been sin ky. Okay. Now when you apply the condition at y equal to a, the potential must be equal to 0, right. So what you get? You get j c1 prime e power minus kx sin k into small a must be equal to 0. Now again here I do not want to make C1 prime equal to 0, because if I make C1 prime equal to 0, then there is no solution for my potential. So I won't make this 0, I can't make J 0, I can't make e power minus kx 0. The only way that you are going to get 0 here is when this Ka actually becomes some integer multiple of pi, okay, for which the constant K, which was earlier unknown to us, must then become n pi by a, and n will be an integer. So n will be 1, 2, 3 and so on. What is the nature of this sine n pi by a? So in general, if I look at the potential that I now can write, potential can be written as some j C1 prime. There is still a constant, don't worry about that one, that gets fixed by the next boundary condition that we are going to apply. This would be sine n pi by a into y. So this n pi by a is nothing but k. If you sketch a few solutions, so let us say this is along the y axis and this is a solution sine n pi by a into y that I am sketching. So you can see that at y equal to 0 and at y equal to a, the potential always has to go to 0. But when n is equal to 1, you can go to 0 with only one half cycle, and when n is equal to say 2, then you need to go in 2 half cycles to 0 or one complete cycle, and when I consider n equal to 3, then you will have to go through 3 times or 3 half cycles. So these are all different solutions, we call them as different modes of the problem that we are considering, but these are all different solutions, and for each value of n there will be a corresponding solution. So now we finally can write, after absorbing j and C1 prime into another constant called C1 double prime, so I can write potential V of xy as C1 double prime e power minus kx sine n pi by a into y. Final condition that I have is that V at x equal to 0, y will be equal to some applied potential V naught. You can take this applied potential to whatever value. So you let us say it is equal to some V naught we have taken. So at x equal to 0, this is the condition. So V0 equal to C1 double prime sine n pi by a into y. Now this actually requires us to understand this one a little bit more carefully. On the right hand side I have a function of y. On the left hand side I have a constant. Now there are of course not one term, there are actually multiple terms that I actually have. So what I actually need to do, and I can't sum up all the sine functions, right? So I can't sum up all the sine functions no matter what value of y to equal this one to V0. But the problem is no more difficult. What this is telling you is that if I consider these as the sinusoidal signals, right? So these are the sinusoidal signals that I am considering. When I adjust the coefficients of each of them, so let's call this as some constant C1, call this as some constant C2. This is n pi by a into y, or rather pi by a into y, okay? And this fellow will have 2 pi by a into y, this will be 3 pi by a into y, this will have a constant of C3. What you are essentially trying to do is that the solution is not just at one particular n, but the solution happens to be the sum of all n, because every n will actually satisfy this condition. So what you are trying to see is that instead of having a single constant and this particular function, what you are trying to do is to take this infinite number of sinusoidal components and adjust their coefficients such that their sum over the range 0 to a will actually be equal to V naught. Okay, this process is very familiar to you in the name of what we call as Fourier series. So what we are trying to do is that you take this infinite number of sinusoidal solutions, okay, so sine n pi by a into y at x equal to 0. So right, at x equal to 0, this is what I am trying to do, and this one should be equal to some V naught. Okay, we will consider this V naught to be equal to 1 volt just to simplify. So I have considered V naught equal to 1 volt. So what I have is essentially a Fourier series summation, and I won't go into the details of how to find this C, and you can look at the textbooks of signals and systems or look at other courses and then just understand how to evaluate this constant Cn. So please remember that what you are trying to do here is you had all these individual solutions, this pi by ay, 2 pi by ay, 3 pi by ay, and then 4 pi by a, and so on, and the sum of all these solutions with adjustable coefficients C3, C1 and C2 must essentially sum up to the applied voltage V0. Here I am just considering the voltage to be 1 volt, and when you do that you essentially obtain a Fourier series coefficient. So y will of course be in the range of 0 to y less than a. Okay. So this, if you now calculate from the trigonometric series or from the Fourier series the corresponding amplitudes of Cn, you get this as 4 by pi e power minus pi x by a sin pi y by a plus 4 by 3 pi e power minus 3 pi x by a. So notice that even the k function that goes into that will also be different. Okay. So sin 3 pi y by a plus something something, right. So you will actually have 4 by 5 pi e power minus 5 pi x by a. So you see that these are only odd harmonics that are going to be present, and you can see that once you substitute, this is the total voltage, sorry, this is Cn is not this one, this is the total voltage V of x y at any point x and y that you are considering. So you see that these are all the sinusoidal solutions, but they all are multiplied by the appropriate amplitude factors, and as x goes to a very large value, so how does e power minus pi x by a vary? It will vary something like this. How does e power minus 3 pi x by 3 pi x by a vary? It will actually vary at a faster rate, and then as you start going for values of higher order and higher order harmonics, the corresponding exponential functions will actually start varying rather rapidly. So which means if I am there at some intermediate value of x, only 1 and 2 or maybe at about the third solution might just be sufficient enough to approximate this infinite series problem into a finite series problem. So with some approximation error, okay, you can retain only a first few terms depending on what value of x I am there at. Okay. After anyway at a large range of x anyway, it does not matter because all the solutions would have essentially gone down to 0, and that is precisely what we want. I mean, we know that the potential at a large value of x actually goes down to 0, but as you go near and near, all the terms will have to add up with considerable amplitude, okay, C1, C2 and all considerable amplitude, such that they will total the applied potential, the applied potential of V0. So this is what we actually can find. So if you now sketch these solutions as in the two-dimensional space x and y, okay, so if you sketch these solutions and then imagine that this actually is your strip, at small values of x you will actually see a larger contribution from all of them, but the contribution will be in such a way that the potential will actually sum up to 1. Okay, so this is the fundamental harmonic, then there will be another harmonic, then there will be a harmonic. So all these are summing up to a potential of 1 volt, but as you go to a very large value, there is essentially only single component sin pi x by a, and the amplitude of this one will also be very small. Okay, here I am just showing it larger for the case of exaggeration, but this will actually be small, and the electric fields will of course be directed in this way, right, which would be perpendicular to the contours of the constant potential. So this completes our Laplace equation in 2 dimension. I hope you really solve these steps and then understand what is going on, and we will solve Poisson's equation in the next module and then consider numerical methods of solving this Laplace's equation. Thank you very much.